Okay, so the last topic we're going to do in our review here is a review of the intermolecular forces. So what the heck does that word mean? Intermolecular, or between molecules. So I'm talking about now, I'm imagining I have a glass of water. I guess we already know that these should be in a tetrahedral. I have a glass of water that's filled with a bunch of water molecules. How are neighboring water molecules interacting with one another, right? That's really what we're talking about with intermolecular forces. So here I have my lone pair on my oxygen is interacting with my hydrogen. This is an example of a hydrogen bond, but that's an example of intermolecular forces. What we're talking about is within a sample, within a liquid here, or even a solid, how are those molecules interacting with one another and how strongly? There are many properties that this affects, how strongly molecules interact with one another. The most notables being this idea of boiling point or melting point, right? That's literally changing the phase where molecules are stuck together and then all of a sudden they melt and they can move around freely. So that has everything to do with how strongly they interact with one another. Boiling point is actually even better than melting point as a sort of indirect measure of how strongly things are interacting, because melting point also has to do with like how they're packed together. Some stuff can pack together pretty efficiently. So boiling point, going from liquid to gas phase, which is really just the process of separating molecules, is a great indirect measure for how strongly these molecules are interacting with one another. So we will be using boiling point and comparing boiling points of compounds sort of as a way of demonstrating that these ones interact more strongly than these ones. So there's three different types of interactions, all right? So molecules can interact with their neighbors in three different ways. One are these dipole-dipole interactions, right? So that has everything to do with what we left off with last video, talking about polar compounds, right? We said that some compounds have dipole moments. So polar, I guess we could say polar molecules interact strongly with other polar molecules. Polar molecules through dipole-dipole. All right. The stronger that dipole moment is, the stronger those interactions would be, right? So the bonds in oxygen, an oxygen-hydrogen bond in water is more polar than a nitrogen-hydrogen bond in ammonia. So water molecules interact more strongly with one another than ammonia molecules do. So yeah, this strength, just how polar that molecule is will let you know how much it interacts. A special example of this is actually hydrogen bonding. So hydrogen bonding is when H is at the partial positive end of a polar bond. Those interact even more strongly than just regular dipole interactions, dipole-dipole interactions, right? So these are, again, just dipole-dipole interactions, but with hydrogen being involved. Those are as strong as you get. And then the weakest ones are what are called these London dispersion forces, okay? London's the name of the guy, not the place, who theorized them. But dispersion forces, what we're going to see is they're very temporary, they're fleeting, and they're not very strong. All right, so let's look at dipole-dipole. This is a good example here of a dipole-dipole interaction that is not a hydrogen bond. So here we have, this is actually acetone. We have this carbon-oxygen double bond that's polar. There's a partial negative charge on the oxygen, partial positive charge on that carbon, right? So this molecule has a dipole moment running right up the middle of it. It will interact with its neighbors through this dipole moment, where the negative end of one dipole is going to want to interact with the positive end of the other dipole, right? Just like charges like to do. Unlike charges interact. So acetone will have these strong intermolecular interactions when this interaction happens, when the oxygen of one gets close to that middle carbon of a neighboring molecule. So this is a good example of a dipole-dipole interaction. When hydrogen's involved, so we just really have the exact same thing going on here in terms of there's a partial positive charge on this guy and a partial negative charge on this guy, and that's why these two things are interacting. But because one of them is in a is hydrogen in a polar bond, it has even that much more, right? So within this bond itself, there's the electron density that's being taken away from that hydrogen atom, giving it that partial positive charge. So that's going to interact even better with this lone pair of electrons over here. Okay, so it's a type of lone pair, or it's a type of dipole-dipole interaction, but you have this hydrogen in a polar bond acting as the positive portion, and then it's almost always a lone pair that's acting as that negative portion. I think it is always. Yeah. All right, and then the last one are these London dispersion forces. So the most important thing to keep in mind about London dispersion forces is this word right here, that they are temporary dipole, or I like this even better, induce a temporary dipole. So let's take a look at this molecule here. These are all carbon and hydrogen bonds. That's what this is supposed to represent. Whoops, hydrogen. We know that carbon and hydrogen bonds are non-polar bonds, so there's no dipole associated with that. What this picture is really representing is just the extremely temporary moment in time when these electrons are all moving around, and for whatever reason, very randomly, some of them end up further on one side of the molecule than the other, right? So it's a very temporary event that happens just because of electron motion. At that moment, when there's that partial negative charge, it will interact with a similar partial positive charge on a neighboring molecule. These are very random, fleeting events, and they're not very strong interactions. So molecules that are only interacting with one another through London dispersion forces have very low boiling points. They'll separate into the gas phase very easily. One key factor with regard to London's dispersion forces is the more surface area. This is one of the key things I want you to have in your mind associated with London dispersion is surface area. The more surface area you have, the stronger those London dispersion forces are. Okay, things that will affect surface area are just the size of the molecule, the length. A long carbon chain has more surface area than a short carbon chain. The other point is compactness, or if there is any branching. Okay, so let's take a look. These are all compounds that have 5 carbons and 12 hydrogens, right? So same molecular weight. The difference here being pentane is in a straight chain. We then have one branching in what's called 2-methylbutane. And we have now all of them sort of branched on the 2,2-dimethyl propane, right? So here the big difference is the amount of surface area. There's more surface area on this end and less surface area on this end because of that branching. And take a look at what happens to the boiling points. As you add the branching, as you make these more compact and decrease surface area, you also decrease the boiling point of those compounds, right? So if you're going to compare two molecules that only have London dispersion forces, the one with more surface area will have a higher boiling point. Okay, so now let's just summarize here. Your dipole-dipole interactions are pretty strong, and they're going to increase with increasing difference of electronegativity between, within that polar bond, right? So molecules that have really big differences in their polarities in their bonds will also have stronger dipole-dipole interactions. Hydrogen bonding, very strong. And this is also going to increase with increasing difference in electronegativity. I guess another thing, oops. Another thing to think about with these is when you have, for example, a nitrogen that has 3 potential hydrogens to be hydrogen bonding, that's better than if you replaced one of those with like this non-polar CH3 group. This, because there are only 2 hydrogens on this particular compound, it's not going to be able to hydrogen bond to its neighbors as well. Likewise, if I removed yet another one, this would have even weaker hydrogen bonding and thus a lower boiling point. And then dispersion forces, they are the weakest. And you want to think surface area. That's how you're going to compare 2 compounds and determine which one has the higher boiling point, is by looking at which one has the most surface area. All right, and then the last, I'm pretty sure, yeah, the last principle that we have to discuss when we're talking about intermolecular forces is this idea of solubility. And so that's, you've heard like dissolving like, but that is whether or not 2 liquids will completely mix together, they're completely miscible, or if you have a solid, whether it will dissolve in a liquid. Polar compounds mix well with other polar compounds. Okay, the more polar it is, the more polar it wants its mixing partner to be. Likewise, nonpolar compounds generally mix well with other nonpolar compounds. And it's really a scale. All right, here all the way on one end, you have polar, over here you have nonpolar, and there's also sort of that gray area in the middle. Everybody wants to only mix with people that are on a similar portion of the scale. Okay, kind of bigoted like that in terms of the polarity world. But yeah, so this is just this idea of solubility, and actually the first experiment we're going to be doing is comparing solubility of different organic molecules. That will again be a video experiment, but nonetheless, so that'll be a good introduction to that. Okay, and so that ends our lecture for this week. Please participate in the various question forums, and don't forget your homework as well. Don't try to do all of the homework all at once. I really don't recommend that. I recommend tackling those mastery ones kind of as you go maybe, and then trying to do the other longer problem set you know, at a separate time. Okay, cool. All right, so I'll see you guys next week.